My name is Yanjun Pan, and today I'm going to introduce our work titled POF, Proof of Falling for Vehicle Platoons. Before I start, let me briefly introduce all the contributors in this work. Ziqi Xu and Juncheng Li are a PhD student from the University of Arizona, and they are co-first authors of this work. Dr. Lucas Lazarus and Dr. Ming Li are their co-advisor. We also have Dr. Nirmesh Ghosh from the University of Lincoln as our co-author. So the broad theme of this work is the verification of physical properties in cyber-physical systems. Especially, we focus on the security and the safety of connected and autonomous vehicles. Our work is motivated by the emerging intelligent transportation systems, especially for connected vehicle technologies, where vehicles can communicate with each other and exchange information such as traffic or velocity. This technology improves the safety of the whole platoon and supports efficient resource use. However, on the other hand, it opens a door to some new attacks, which we are going to introduce later. A prime application of connected vehicle technology is cooperative driving, where the vehicles can drive cooperatively with cooperative adaptive cruise control by changing some wireless messages. Seeing that if we set a short time gap, like 0.3 seconds, when the car is driving at the speed of 16 miles per hour, then we will have the distance between two vehicles to be 8 meters in this case, which gives us a time times reduction from 3-second rule when the vehicle is driving manually. Another important feature of platoon is that the formation is dynamic. Consider a two-vehicle platoon. The verifier should be able to let the candidate vehicle to join the platoon when the request is sent. Once this candidate is accepted, it can inject his messages into the platoon and have some control over the system. So in this case, the trust establishment among all the vehicles is very important for the security and safety of the platoon. First, let's see how the verifier can verify the identity of the candidate. First, we assume that the identity of the verifier can be known by the candidate with public key cryptography system. Then the candidate can encrypt its message with the public key of the verifier, followed by its signature and certificate. In this way, the verifier can verify the digital identity of the candidate. However, the main issue here is that how does the verifier can know that the candidate is platooning actually, since there is no way to bind the digital identity of the candidate with its physical location. And this property of the platoon opens a window for the attacker to join the platoon without even following it. This figure shows an example of some attackers. First, we can see that for a remote attacker, it can send requests to the verifier with critical infrastructure. Similarly, we can have roadside adversary and following of our adversary send requests to the verifier. And all of them can be joined into the platoon since all of them have valid digital credentials. Furthermore, those attackers can even join multiple platoons without following any of them. So from that example, we can say that the crypto itself is not sufficient to verify the physical properties in platoon, such as the location, proximity, time or speed, and so on. And in practice, we do need to have some method to verify the physical properties to secure platoon. To this end, we propose the concept of proof of falling. That is, given a route of V and C, the distance between V and C need to be bounded by the reference distance dref at any time of the route. In this way, it gives us a method to have a physical access control, such that only platooning members that are actually following the platoon can communicate with other vehicles and have control over the platoon. Our strategy is motivated by a simple scheme called I spy with my little eye. The idea is that for two vehicles that are driving closely, they should be able to observe a similar environment. Such environment can be vision or sounds according to the availability. Then, with the common context, those two vehicles can exploit it to prove their falling status. But the key here is that the selected modality must be dynamic in terms of spatial and temporal domain. That means such modality need to change during the driving, and the measuring opportunities should change over time. Especially for our work, we use RF modality, and we use large-scale fading. We select large-scale RSS is because the hypothesis is that for two vehicles which are drive closely, they should observe similar large-scale fading from the signals received from the LTE tower. The reason we choose large-scale RSS is because the theory tells us the spatial correlation between those two vehicles decreases with their distance. And this figure shows this relationship. The y-axis is the correlation coefficient of the RSS received by V and C, and the x-axis is their distance, where we use a normalized distance by normalizing it with decorrelation distance. And this decorrelation distance can depend on the environment. So from this figure, we can see that the spatial correlation does decrease with distance, and it decreases exponentially. Besides, the temporal correlation also decreases with time, and such modality properties can be measured just using existing receivers, so that no extra hardware is needed. We validated this hypothesis with experiment on freeway, and those three figures show the result, where we can observe this decorrelation relationship with distance and time, just as we expected. Here we show the simplified POF protocol, where the candidate first sends a request to the verifier to join the platoon. The verifier will verify its digital identity, just as we explained. Then the verifier sends a synchronization signal to the candidate to tell the candidate the timing for the RSS collection. With that timing information, both the candidate and verifier can collect the RSS. Then the candidate sends its RSS to the verifier to compute the correlation. The decision is made based on the computed correlation, either to accept the candidate or reject it. In fact, our protocols is done with several steps. Consider two collected RSS values, gamma C and gamma V. We partition gamma C and gamma V to K subsets of size n. Here, our Our verification is based on multiple tests, where this K is the total number of multi-tests. Then for each subset, we compute the correlation based on M-point moving average to get the large-scale correlation. If this correlation is greater than the threshold tau, then we say that a single test is passed, and the candidate will only be accepted after it passed a portion of alpha tests. We did the experiment validation with a vehicle testbed, and this testbed is set with have different setups according to different environments. The first setup is for the freeway and the urban, where those two vehicles are manually operated with cruise control. And the second setup is for highway, where the verifier is operated with cruise control and the candidate is on adaptive cruise control. And we drive at a speed of 55 to 16 miles per hour. This figure shows our hardware layout, where we use a laptop to control all the hardwares, and the RF modality is received by the USRP control powered by the power supply. The vehicle location is provided by GPS controlled by the smartphone. As our protocol relies on several parameters, so we talked about how to select those parameters with the preliminary results. Here we focus on the number of the samples N and the moving average window size M. For this figure, the y-axis is a correlation and the x-axis is the following distance. First, we can see that for both N and M, for the given following distance, the correlation increases with the increase of N and M. But the benefit diminishes eventually. So in our analysis, we set N to 400 and M to 20. Here we show the experiment results for the highway, where we consider the pre-recording attack, where the attacker drives on the same road ahead of some time for the candidate. And for those two figures, the y-axis is the passing rate, and the x-axis is the number of the multi-test. For both pre-recording attack and falling of our adversary, we can see that the adversary's passing rate goes to 0 when the number of the multi-test increases, while the candidate's passing rate goes to 1. We have similar observation with the environment done in the urban environment. In practice, it is also possible to have man-in-the-middle attack, where the attacker puts itself in the middle of the communication between the candidate and the verifier. In our paper, we propose a man-in-the-middle resistant POF protocol, and you can find more details there. Our results did show that the proposed RSS-based POF is effective when the distance between the candidate and the verifier is close. But it also has some limitations. It cannot verify the relative order of candidate and verifier, and it cannot verify the driving lane. But those two issues have been addressed in our followed work. In conclusion, in this work, we developed a POF protocol to enable the verifier to verify the falling status of the candidate. And especially, we explore large-scale fading property as a new modality. And we demonstrated the security of our protocol under different types of attacks in different types of the environments. Thank you for listening, and I'm happy to take any questions.
All right. Let's thank our speaker.